talking about angles within circles. Now we're breaking away from angles and doing segments in circles and their properties. So for the past couple of days, we've been focusing solely on angles. We are breaking away from that and now looking solely on segments. All right, so you want that circle, that journal that looks like it has a circle in it. No other one. Yeah. All right. So for the next couple of days, or the next 2 days, so today and then Monday, we're going to talk about the different types of segments dealing with circles. This is technically our last lesson. All right. So after we do these, we will talk about, we'll review Tuesday, test. What? Under the table. So after we do this, we will do review Tuesday and then test Wednesday. All right. All right. So again, go ahead, throw anything to do with angles, kind of compartmentalize it somewhere in your mind, save it for later, but we don't need it for today. All right. So we are now focusing solely on the segments. So this has to deal with the lengths of the segments of either chords or lines built within the circle. All right. So there's a couple of theorems that we have to talk about first. The very first theorem is in a circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if we look at this circle here, based off of the tick marks, which two sides are congruent? The ones on the left and right or the ones above or below? So remember, with tick marks, you match them. Mariana, since you're up, can you turn the light off, please? So am I talking about, by tick marks, I mean these little tiny lines here. Remember, if they have the same number of tick marks, they are considered congruent. So which are my two congruent sides? So to make things easier, let's call this quadrilateral A, B, C, and D. So which two segments are the congruent ones? A, B, and D, C. Good. So since AB is congruent to CD, all right, since these two segments right here are congruent, that means that the arc AB is congruent to the arc of CD. We're talking about their arc measures. So that means that these arcs right here, AB and CD, are also congruent to each other. Now, they're not the same length as the side themselves. They just have the same measure. All right. So you have to have this statement in order to get this statement. So if you have two congruent segments within a circle, that means the arcs that they form, or basically between their 2 points, the arcs on the circle, are congruent. All right. That also works in reverse. If you have congruent arcs formed by two segments, that means those two segments are congruent. All right, so it works in reverse as well. The second theorem is in a circle, if a diameter or radius, it doesn't matter, is perpendicular to a chord, then it bisects the chord and its arc. So remind me, what does the word bisect mean? We talked about this back in Unit 5. It means cut in half. Cut in half into two congruent pieces. All right. So that means this radii right here goes from center to radius. It's not congruent, it's perpendicular, forms a right angle with that chord. That means that it bisects the chord. So that means this little tiny piece of the chord is congruent to this little tiny piece of the chord. Now, where this comes into play is that a lot of times you'll be asked to find side lengths based off of those chords and the radii. So what you typically do is that in problems like these, typically what you're going to have to do is draw two more radiuses or radii to connect to the endpoints of the chord. All right, and since they're radii, they will be congruent to each other. Now, if we draw a radius to make a right triangle, all right, that typically means we're going to use what if we're solving for side measures? What do you think we're going to use? A very specific theorem that you've been learning for years and years. Pythagorean theorem. So a squared plus b squared equals c squared will be used somewhere in here. Now, it's also fair to note that that radii also bisects the arc that the chord makes. So that means this little piece of the arc is the same as this little piece of the arc. So it bisects both the chord and the arc as long as the chord and the radius are perpendicular to each other or form that right angle. All right. Then the last part. In a circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. What does equidistant mean? Equal distance, same distance, however you want to put it. All right. So, in other words, these two chords right here are considered equidistant because if they drew a line directly from the chord to the center point, it has to be perpendicular to that chord. It's like a direct shot. They should be congruent. If they are, that means they're equidistant. Now, more often than not, whenever this happens, so again, this means that the green chords are congruent because they are the same distance from the center. Now, where you'll see this a lot when you're trying to find chord lengths is that you're going to have to use Pythagorean theorem with this as well. So more often than not, you can always draw a radius from any point, especially if it goes past the center. So a radius, as long as it goes through the center, it's considered a radius. So more often than not, a pro tip here is that if you're ever finding a side length Like say you're trying to find how long this little piece of the cord was, and you knew the radius was so long, you can always make a right triangle and use Pythagorean theorem, which you will see some questions like that. So basically, drawing a radius makes a right triangle. So anytime you can draw a radius, it will make that right triangle. Now, those are not all the theorems that we're going to discuss, but these are actually the easier ones or the more basic ones. These specifically use Pythagorean theorem for most of it. All right. So let's actually do some example problems, putting that into action. Yes. Yeah. So look at number 1. If segment AB is equal to 5x and CD is equal to 3x plus 6, we need to find the length of AB and CD. So, based off of the information that I have given to me, I'm going to go ahead and label AB is 5x, CD is 3x plus 6. Now, look at the information that they give us. Which theorem do you think I'm going to use? The first, second, or third theorem on this page? Not the third. First. Why is it the first? I'll give you a hint. Look at the arcs. They're equal. So remember, if two arcs formed between a chord is congruent to another arc formed between another chord, that means the chords are what? They're congruent. So both of these chords are congruent to each other. Thus, what will be the easiest way to solve for x? If the chords are congruent to each other, what's the easiest way to solve for x? So now we're just dealing with the segment lengths. So 5x and 3x plus 6. The arc degree just told us that they were congruent arcs. That's all we need the arc degree for. So how do we set up our equation to solve for x? Set them equal to each other. So I have 5x is equal to 3x plus 6. So once we determine that those chords are congruent, we can essentially ignore these arc measures. So if it helps, you can even cross them out because you don't need them anymore. All right, they serve their purpose. So let's solve this equation. We're going to subtract 3x to both sides. That goes away. 2x is equal to 6. What's my last step? Divide by 2. So x is equal to 3. Now, x equals 3 is not my answer because what did it ask me to find? A, B, and B, C, D. They want the actual side lengths. So what do I need to do? Plug the x back in for one of the x values here. Why do I only need to plug it into one? Because they're congruent. So you can plug it into both if you want to, just to check to see if you're right, but they should both equal the same thing when you evaluate. So since segment AB is congruent to segment CD, that means they equal. Which one do you want to plug it into? The 5x or the 3x plus 6? Definitely the 5x. So if we do 5 times 3, what's that equal to? 15. That's our answer. And if we want to do a quick check, we can plug it into the other one to make sure it's equal to 15. 3 times 3 is 9, plus 6 is 15. So it works. So make sure you read the question very carefully because sometimes they tell you to solve for x, but other times you have to solve for x in order to solve for the side length because you'll end up having to plug it back in. So make sure you read the questions very carefully because that's where a lot of people can get points taken off on, say, for a test because they solved for x correctly, they just didn't go and plug it back in. All right, so make sure you're solving for what you need. All right, any questions on number 1? All right, number 2. All it wants us to do is find the value of x. So we're solving for x, which comes from this right here. Now, within this quadrilateral, these numbers are not angle measures. They are side lengths. How do I know they're side lengths and not angle measures? What are they missing? There's one symbol that they need in order to be an angle measure. They need a degree symbol. So that's how you know if they're side lengths or angle measures. If they don't have a degree symbol, they're side lengths. All right. Now, I have congruent sides somewhere within that quadrilateral. Which two are the congruent ones? (12x minus 2 and 34. Those are the congruent sides, but why are they congruent? Because what? The arcs that they form are congruent. So since these two arcs are congruent, they're both 80 degrees, that means the segments that formed them are congruent as well. So knowing that, how do I solve for x? Set them equal to each other. So this is a classic example of a problem that gives you too much information. All right, you don't actually use every piece of information in this problem. You just need to use what they ask for. In this case, we're solving for x. So since we can determine that these two segments are congruent based off of the arc measures between them, that's the only two pieces of information we need. So we don't have to worry about the 78 or the 56 or the 50 or the 150. Those are irrelevant to us. All right. So if I solve this, I would add 2 to both sides. 12x is equal to 36. Divide by 12. X is equal to what? 3. And since it told us to just solve for x, that's all we have to do. Now, what's a good way to check myself to make sure I got the correct answer? What measure does 12x minus 2 have to equal to? 34. So to check yourself, do a quick plug back in the 3 in for x and evaluate, which that would give us 34. Any questions on number 2? All right. Numero 3. Now, given that the chord BC is 15 centimeters from the center of the circle A, which has a radius of 25 centimeters, find BC and DE. So that was a lot of information. So let's talk about it. So what they said is BC, this entire segment BC is 15 centimeters from the center. Oh, I read that wrong. See what I mean? So it's 15 centimeters from the center of the circle. So which segment would I use to describe the distance from BC to the center? So we're looking from how far away BC is from the center of the circle. So what segment describes that? I'll give you a hint. One of the points is going to be the center. AD. So from the center to hitting segment BC, we use the point AD. So this right here is 15 centimeters. Now, the radius is 25 centimeters. So where would I mark that radius as 25? So what segment do I mark as 25? BA. There's somewhere else I can mark it to. Where else? Not AC. We don't really need AC. We could, but we don't need it. But there's one that's already marked that we can mark it. AE. So if we combine A and E, that would also equal 25 centimeters. So, based off the information we're given, we're trying to find BC and DE. One of those segments we can find very easily. Which one do you think? So one we can find very easily without having to do any fancy calculations. Which one do you think we're going to do? So look at the locations. BC is right here. DE is right here. So I ask again, which one do you think we're going to find the easiest? DE. Why DE? Right, we already have two parts of the segment. Since segment AD plus segment DE is equal to the length of segment AE, because it's just two different pieces of it, that means I can take whatever the segment length is for AE and subtract the segment length from AD to get DE. So I would do 25 minus 15, and that's equal to what? 10. So 10 centimeters is equal to DE. So this first part right here is 10 centimeters. Now, what can I use to find BE? Or BD, sorry. Pythagorean theorem. We have a right triangle here, so we can use Pythagorean theorem. So again, that would be a squared plus b squared is equal to c squared. Now, how would I set it up using the Pythagorean theorem? Someone besides Jasmine. So remember, what always has to be your c value in a right triangle for Pythagorean theorem? The hypotenuse. Which one's my hypotenuse? The 25. So this is my c. A and B can be either one of these. So we're just going to do a plug and chug. So I would get a squared plus 15 squared is equal to 25 squared. So I get a squared plus 15 squared is 225 is equal to 25 squared, which is 625. Subtract the 225 from both sides. I get a squared is equal to 400. What's my last step? Take the square root of both sides. So, what's the square root of 400? 20. So, BD is equal to 20 centimeters. So, again, for most chord problems, more often than not, you're going to end up using the Pythagorean theorem. All right. So, you guys should be fairly decent at Pythagorean theorem by now because you've been seeing it since Math 1. All right. All right, let's try another one. Let's look at number 4. So it wants us to find AD, CD, and the measure of arc AB. So Think about this carefully. What's something that they've already marked for us that could be very helpful in finding one of our measurements, Landon? The center what? The center angle or the central angle, which is this 60 right here. Why is that important? What's true about central angles? How do central angles relate back to their arcs? Not half of it, that's inscribed. This is the very first thing we learned about angles and circles. It's the same as the arc, they're congruent. So that means that's intercepting arc, or right here, is going to be how many degrees? 60 degrees. Now, that being said, we know that if a radius, which is CE in this case, cuts an arc perpendicularly, which is AB, what's true about that chord now? So if it cuts the chord perpendicularly at a perpendicular angle, what's true about that chord? This is the second theorem we talked about. They bisect each other, which means to do what? Cut it into equal pieces. So these two segments are congruent to each other. What's also true, it doesn't just bisect the chord, it also does what? It bisects the arc itself as well. So AE is 60 degrees, which means BE is what? 60 degrees. They're congruent. Thus, the measure of AB is equal to what? So we have two equal pieces. And those pieces make up the entire arc of AB. So how do I find what that arc measures to? You just add them together. So what's 60 plus 60? 120 degrees. So this arc right here is 120 degrees. All right. Now we got to find ACE, AD, and CD. All right. So there is a theorem that we can use to find these in one fell swoop that's actually not Pythagorean theorem because we don't have enough information to do Pythagorean theorem. Why can we not do Pythagorean theorem? Right, you got to have at least two sides in order to do Pythagorean theorem. But we can use another special property of a right triangle. Which one do you think that is? You guys remember back in math too with your special right triangles? Do you guys remember a 30, 60, 90 triangle? So, if we look at this triangle, is it not a 30, 60, 90 triangle? So we got one angle that's 90, one angle that's 60. So that means this other angle has to be what? 30. So we do have a 30, 60, 90 triangle. So that being said, we can use the special right triangle for a 30, 60, 90 triangle. And just to recap, the formula is as follows. So this is the, let me make this bigger. So this is the 30 side, this is the 60 side. The side that's opposite from 30 is known as the what? So it's known as the short leg because it's shorter than the other leg. So let's call that leg A. The side opposite from the 60-degree angle is called the long leg. And the way that it relates to the 30 is it's A square root 3. So A times the square root of 3. And then the angle directly opposite from the 90-degree angle is obviously the hypotenuse. And the way it relates is that it's 2 times the short leg. So these right here are all the ways that we do with our triangle. So, in other words, everything connects through the short leg. All right, there's no direct path from the hypotenuse to the long leg. You got to go through the short leg first. So, that being said, if I'm looking at triangle ACD, what side did they give me? They gave us the hypotenuse. All right. So, which side measure do you think I should find first, CD or AD? So we need the short leg. We got to find the short leg next since we have the hypotenuse. Which side is directly across from the 30-degree angle? CD. Since this one's across from it, this is our short leg. This is our long leg. So if the hypotenuse is equal to twice the short leg, that means the easiest way to find the short leg for CD is to do what? So if the hypotenuse is twice the short leg and my hypotenuse is 6, how long is the short leg? So guys, how do I get from A to 2A? What do I do? Not 2 times 6. So remember, we're going from hypotenuse to short leg. So how do I get from 2A to A? You divide by 2. So I got to do 6 divided by 2, which is 3. So CD is equal to 3. Now, AD is our long leg. So if our short leg is 3, remember, to go from my short leg to my long leg, all I got to do is multiply the square root of 3. So it's very easy because all we got to do is just write 3 times the square root of 3. And that's our length for AD. So all those special right triangle theorems can come back to haunt you. All right. So I would definitely, if you didn't already, take note of this. All right. This is a Math 2 concept. All right. Last little bit, and then we'll take a break. So in circle A, FG is equal to 3. GA is equal to 5. AH is equal to 4. And they want us to find PJ and LA. So firstly, let's label what they gave us. So segment FG, which is this segment right here, is 3. GA, which is this segment right here, is 5. AH, which is this segment right here, is 4. And they want us to find the length of PJ and the length of LA. So, first things first, LA is going to be really easy to find. Why? Well, it's not necessarily just doubling. Yes, we can assume that it is doubling, but we don't know for sure. Now, we could continue gx here and make the radius, which, since it intersects at a perpendicular angle, yes, we could double it. All right. So, and the reason we know that is because PG and AG are both radii. So PG and GA are radii. Now, since they're radii, what does that mean PG has to be equal to? PG has to equal what? The same thing as GA, which is 5. Now, the reason I can't just assume that these are equidistant from each other, or that these are the same, like if you draw all the way a form a radius, we just can't assume it. We got to use the information that we got. But I can now do what to find this little segment right here? What can I use? Pythagorean theorem. All right. So if I do PF, that's equal to 3 squared plus b squared, which is 5 squared. So this would be 9 plus b squared equals 25. Subtract the 9, I get b squared is equal to 16. Square root it. B is equal to 4. So PF is equal to 4. Now, let's say I drew a radius from J to G, which you can do. That you definitely can do. That means that that radius would also be 5. So if I have two sides, one of them is still 3 and the other one's 5, what obviously has to be this little segment right here, JF. We just did the calculation, right? It's 4. So now for sure we know that these two little segments are congruent. So PJ is equal to 4 plus 4, which is 8. Now, is PJ congruent to LA? That's my question for you guys, and how do you know? Yes, how do you know? I'll give you a hint. Theorem 3. Right, they're equidistant from the center. So these are both the same distance. All right. And the reason we know that is because this should also be 3. All right. Because if this side right here is 4, it's basically implying that this has to be 3, because if we replace 4 and leave out the A, you'd still get the exact same thing. You're just working backwards. So PJ is equal to 8, and it's congruent to LA. So that means they're both equal to 8. So these two sides are congruent to each other. All right, last one for today, and then I'll let you guys work. This one's quicker. All right, FG is equal to 3x minus 4. HJ is equal to 14. Find the value of x. So FG, which is right here, is equal to 3x minus 4. HJ, which is right here, is 14. So what's the easiest way I can do to find the value of x? It's very straightforward. Set them equal to each other. Why can I set them equal to each other? Landon. Right. Do you see how these both have little 2's here? That means from the center to that chord, they're both about 2 units from that chord. So since they're equidistant, that means FG is congruent to HJ, which means that FG should equal 14. So to set it up, we have 3x minus 4 is equal to 14, and then we can solve. Right? Add 4 to both sides. Okay. Yep. And that's exactly how you do it. So guys, with these, it's all about picking the right theorem and then rolling with it. Now, we're not done with segment theorems, but we'll pick this up on Monday. All right. So there is a new delta math, but I don't know for sure if you can do it all yet because we haven't covered, because plus the other journal that I gave you, there's one more too. So we'll pick this up on Monday. So you guys can have your 5-minute break. When you come back, you can work on delta maths or catch up on work. And I'll go ahead and post the exit ticket as well.